doesn't really matter. I'm just curious if you even know what I posted, and it's obvious to me that I would say that most of you do. So that's good. I don't really care if you watched it all. I had one person comment on it. So I don't post a lot in the announcements, but anyways. So example 1, area. We're going to use the definition of the area of the region and the plane to set up the calculation to find the area under this curve. So would you guys do me a favor? Would you please try to set this one up? This is exactly what we're not going to actually do it. I just want you to set it up. So just one more time and then we're moving on. All right, so my guess is most of you guys remember this is the formula that I just wrote it, and you probably looked it up or figured it out on our last example. What is delta x here? It's 4 over n, right? That's what our delta x is. C sub I. 4 over ni. It's not starting at 0 though, folks. So what now? Anybody know? Anybody know? How do we fix this? And you say, wait a minute, Mr. Young, you just told us you're never going to ask us that. I'm not actually going to do it. I just want to show it to you one time just to make sure, just in case someone's super eager. Any takers out there in calculus land? So if this had been 0, you would just leave this as is. Just what do you think you're going to put right there to make it not start at 0? Just 1. Now you might say, well, Mr. Allen, you're a dirty dog. That seems so easy, right? Here's what I'd like to show you, though. I want to show you this now with all this substituted in. So this is going to be the limit as n goes to infinity. We're still doing the sum from 1 to n. And now we're going to have 2. And then in parentheses, this is where we're going to write that red stuff. It's going to be 1 plus 4 over ni. And then let's go ahead and go back to, I was using blue, I guess, plus 5. And then over here in red, I got to write this guy again. So this is 4 over n. Now, guys, when you look at that, does that look a lot more difficult than what we've been doing? The answer is really not, but I'm telling you it is. I'm telling you, for whatever reason, if I start putting this little guy in there, students, they already struggle with the algebra. This extra little piece just makes it to where most students just really struggle on getting this. And my goal is not to make you guys just totally hate math, right? So anyways, this is what you would set up. And I'll let you know that the final answer here turns out to be 44. And by the way, you could have done that without calculus, because what kind of function is this? It's linear, right? So it's going to make a trapezoid like that one I talked about yesterday. So you can check that. The answer is 44. But anyways, I'm going to move on now to today's stuff. All right. So we're going to talk about Riemann sum. So here is the definition of a Riemann sum. I'm not going to spend a lot of time on it, but it's basically a partitioning of the interval. It just means you're cutting the interval up into smaller little pieces. And what we're going to do, look at does this look familiar right here? Does this formula right there look familiar? It's the exact formula that we've been talking about, except it doesn't have the limit stuff. Notice it doesn't say LIM in the front of that. It's the exact same thing we've been doing. So you've been doing Riemann sums. I just didn't tell you you were. And by the way, Riemann was a famous mathematician. He actually only wrote one paper on math that I'm aware of, but it's considered one of the most important papers ever written. And there's something called the Riemann hypothesis. And guess how much it's worth if you figure it out? $1 million. So if you are interested, if you can figure out the solution for or proving the Riemann hypothesis true, you get $1 million. So anyways, there's some, you ever think math doesn't get you anything? There you go.
Yeah, but who gives me the $1 million?
The Clay Institute. Yep. Okay, so now let's do an example. So here it says Riemann sums to approximate. So remember, I'm going to go back to this. Remember, the Riemann sum here didn't have really anything to do with the limit. So what I'm going to do now is I'm going to use Riemann sums to approximate, and I want to be very clear about this. So we're actually now we're going to go back, and I'm actually going to make things a little bit easier. Okay? And you might say, Mr. why are we spending more time if we've already done the harder stuff? Because they actually will ask you questions like this on the AP exam. In fact, I will ask you questions like this. It says use left and right Riemann sums to approximate the area under this curve. Here's the curve. I just used Desmos to draw it. From the So in this example here, I'm going to use left Riemann sums. I'm going to use left on this one. And then when I go to the next slide, guess what I'm going to do? Right Riemann sums. So what the heck is a left Riemann sum? Here's all it means. If I said to do a left Riemann sum, it means you measure on the left. By the way, we went from 0 to 4, correct? How many rectangles do you see? How many subintervals does it say we're supposed to have? And by the way, notice that each of my rectangles, I measured it on the left. Now notice what I did is I made the height of the rectangle go from the x-axis up to the curve. So these are the left Riemann sums. Does that make sense? Okay, so I'm going to go to this one over here. Now I'm going to do, and I actually haven't done anything yet, but I'm just going to draw them first. I'm going to do right Riemann sums, okay? So instead of measuring on the left, guess where I'm going to measure? I'm going to measure on the right. So this time I'm going to do this. And guys, I know I'm not doing a perfect job here, but I'm not really worried about doing a perfect job. I just want you guys to get an idea of what I'm doing. By the way, how many rectangles do I have again? Here I measured them on the right edge of the rectangle. Over here I measured them on the left. You will notice that all of these rectangles are under the curve in this particular example, and all of these happen to be over. Okay, so now let's actually do the calculation. Let's start with the left. Okay, so to do the left, by the way, what's this length right here? That's 1. What about this length? They're all 1, aren't they? Remember, the area of a rectangle is length times width, or base times height. Agreed? So that's 1, that's 1, that's 1, and that's 1. How am I going to find the height? I'm going to use this lovely table that I just conveniently put in the PowerPoint here so I don't have to figure it out. So I want to find this height. Well, that's equivalent to when x is 0. And what's the height? So this is 3. What's the next height? Well, it'd be when x is 1, right? So what's that? So that's 3.5. What's the next one? 5. And the next one? 7.5. In other words, this area is, oh, and by the way, notice I'm not using an equal sign. Why am I not using an equal sign? Well, hopefully you're smart enough to realize those rectangles don't actually add up to the exact area, right? They're an approximate area. So what I'm going to do, in fact, if I wanted to, is I could literally take this right here and write it out, but I'm not going to do that now, is I'm just going to say it's 1 times 3 plus 1 times 3.5 plus 1 times 5 plus 1 times 7.5. And just to speed that whole process up, the final answer here turns out to be 19, if I'm not mistaken. Agreed? So and by the way, would you guys agree that is not a hard thing? This is not hard. That algebra we did earlier, that was hard. This is just, can you multiply and add some numbers together? By the way, a point I'd like to make, what operation did I do between each of these? Addition. What operation did I do between each of these? Oops, over there. And by the way, that corresponds to this formula right here. What does this mean? Repeated addition, right? What's the operation between this piece and this piece? Does that make sense? This is the compact way of writing all of that. Okay, let's do the same thing with a right Riemann sum. Now we're doing the right Riemann sum. So all of these, again, have a base of 1, right? What's the height of the first rectangle, though? It's now not 3, it's 3.5. What's the height of the second rectangle? 5. 7.5. What about the last one? 11. So this area is approximately, well, it's going to be 1 times 3.5 plus 1 times 5 plus 1 times 7.5 plus 1 times 11. And that one turns out to be an answer of 33. Oh, that doesn't seem right. 26, thank you. That's not right. That's clearly not right. 26, thank you. Where'd I write there? I wrote 33.
Oh, yeah, that's 27.
27? Okay. Help me out here, guys. It shouldn't be that hard. I should be able to do this in my head, right? If we add these two together, you get 11, 22 plus 5. Yeah, it's 27. Okay, thank you. By the way, where do you think this is this the correct answer for the exact area?
No.
Is this the correct answer for the exact area? Where do you think the answer is? It's somewhere between those two, though, isn't it? Because all these, so this is let me do this in red. This is an underestimate. This guy over here was an overestimate. And just to let you know, in fact, let me do that now let's do this in green. The exact answer, and by the way, this is correct. The exact area is 22 2/3. And by the way, hopefully you realize that that's bigger than 19 and less than 27. Does that make sense? Now, let me stop here for a second. Does anybody have any comments or questions on using left or right Riemann sums? Okay, so I guess the final thing I want to say about Riemann sums is this. These are not the only options. Typically, it's either left or right. There are some examples that I've seen on the AP exam where they'll ask you to use midpoint Riemann sums. How would you do that?
Put the middle of the rectangle.
Instead of using 0 or 1, what would you have to use for this first rectangle? You'd have to use x equals 1/2. By the way, is the idea the same? It's just they've added one little extra piece, and it turns out that the midpoint is actually typically a little bit better approximator than either the right or the left. Okay. The other thing I'd like, so there's 1, 2, and there may be even more than that, but there's at least 3 that I can think of. And then there's one more thing I want to mention. You notice in this example how I said they had to be equal length subintervals? Please do not assume that that is always the case. That is not always true. It does not have to be true. Okay, so I've mentioned those things so that if we ever run into those in the future and you, so that might be a good thing to write down for notes. It does not have to be equal subintervals. Okay, anyways. All right, so very, very important slide for a couple of reasons. Before I get to this part over here, this piece here should look pretty familiar, doesn't it? Except for one little thing. Do you see that it has vertical bar, delta, vertical bar, 0? What the heck does that mean? Let me explain what it actually doesn't mean absolute value. You guys are, what are you guys used to seeing down there? N going to infinity, right? Now, let me just kind of briefly explain what this is. And guys, I'm not asking you to, I don't care that you know this particular one. What this is saying, how many, let's focus on the N. What did the N represent? How many rectangles, correct?
Yeah.
So N could be 4 rectangles like in our last example. And then if we want it to be more accurate, we increase N, we increase N, we increase N to infinity, right? And that gives us the exact area. But here's my question. As the number of rectangles increases, what happens to the width of those rectangles? It's going smaller and smaller and smaller. In fact, it's going towards 0. It's what we call an infinitesimal. So that's what this is saying. This is telling you that the width of the rectangles is going to 0. It's not 0. It's going to 0. Which is equivalent to this, okay? So in other words, what I'm trying to convince you of is, have we kind of already discussed this in some good detail on the last day? Yes. Now, here's the connection. Instead of writing all this stuff, which honestly, how many of you had never even seen that before you came to this class? How many of you have seen something that looked maybe like that, though? This is what we call the definite integral. Now, let me go back to section 4.1. I would have said something like this. Oops, got to get a variable in there, not D first. Let's get an X in there. I would have maybe given you something like this, right? And I would have said, what is the solution to this indefinite integral? What would the answer be? Sine X plus C, right? That was an indefinite integral. This is the definite integral, and guess what its answer will represent geometrically? It's going to be a number. And guess what that number represents? Area under the curve. Now, guys, I'm giving you all the conceptual stuff before we do the fundamental theorem of calculus next week. I'm trying to build the foundational conceptual understanding of what this definite integral thing means. So I'm telling you, like up here, this integral gives you a function, right? The definite integral is going to give you a number. And guess what that number represents? The area under the curve. One final thing here before I go on to my next example here, and let's see how we're doing on time. We're doing great. What if I said, what is f prime of x when, let's say f of x is equal, let's keep it super simple. Let's say it's 2x. What is f prime of x? Actually, oh, that's not a great example. Let's do this. Let's make it a little bit more interesting. What is f prime of x? 6x squared, right? So that give us 6x squared. I went from this, and what did it give me? It gave me a function, correct? You with me? Okay, but what if, instead of asking that, what if I said, what's f prime of 0? What's that? That's not a great example. In fact, it's not a great, it's 0, right? What does this mean? This is the actual slope of the tangent line, isn't it? So there's a connection somehow between differentiation and integration. I could ask you to find the derivative, the general derivative, and it gives us a function. Or I could ask you to find the actual derivative at 0, and it gave us a numeric value, correct? Similarly, when we use integration, I could integrate the indefinite integral, and I get a function. Or I could do the definite integral, and guess what it gives me? A number. Okay. Now, the next slide here, I need to make an important point. This is an area, correct? And let's just say that that area is, I don't know what it is, but let's say it's 4, okay? What would you guess this area over here to be? Based on that, 8 maybe, right? So this area is 4, and this area is 8. Is that okay? Do you guys believe that kind of? Guess what happens, though, if you just do the integral from here to here? Guess what kind of answer you're going to get? It's not going to say 8. It's actually going to say, do you know why it's going to say -8? Because this area is under the x-axis. This is going to give you an answer of 4 because it's above the x-axis. So we need to be very careful. I'm telling you that you guys might do a problem like in this case, I'll just say it's -2 to 0 of some function, and it's going to tell you the answer is -8. Area can't be negative. What's the smallest area could be? 0, right? It could be 0. That's the smallest it could be. You can't have negative area. But when you do integration with the definite integral, it's going to tell you -8 in this example. And guess what that means? It just means it's below the x-axis. Okay, does that make sense? All right. All right, here's a whole bunch of properties. And I claim that they are all important. You need to be familiar with all of these. Next week, when we move on to the fundamental theorem of calculus, these things will help you find definite integrals with or without the fundamental theorem of calculus. And by the way, all of these are in the notes that are already on Canvas. Okay, here's the first one. First one says this. If you ever try to find the area from A to A of a function, it will always be 0. Guys, if I ask you to find the integral from 0 to 0, guess what the answer is going to be? 0. Because guess, if you go from the same place you're starting to the same place and you end the same place, how much area could you have? You didn't go anywhere. It's 0. So that's what this one's saying. It's saying if you integrate from like 2 to 2, the answer is always 0. In other words, if you start here and you end at the same place, it's 0. This one is very handy as well. These are called the limits of integration. These are called the limits of integration. And in this case, the lower limit is B and the upper limit is A. In other words, we're going to start from B and we're going to go up to A. In this example, actually, here, let me go back to what I had originally. I think I went from -2 to 0, right? Where did I start? -2. Where did I finish? 0. So this is my lower limit of integration, and that's my upper limit of integration. It turns out that if you switch these, now notice that B went up here to the top and A went down here to the bottom, that you're going to get negative. Let me explain that one a little bit further. So over here, we said the answer was 4, right? So the integral from 0 to 1 of our function f is 4. Agreed? Guess what the integral will be from 1 to 0 of f of x dx? Since I switched them around, it's going to be -4. So what I'm telling you is when you integrate, not only does it matter where the curve is in terms of the x-axis, it also determines if you're moving from the left to the right or the right to the left. Okay, now the rest of these are pretty, I think, intuitive. If you want to integrate from A to B, so let's say I've got some curve that does this. Let's say that this is at A and this over here is at B, and I want to integrate that whole curve. Let's pretend that there's some point here in the middle. Let's call this point here C. And I want to find the area under the function f of x all the way from A all the way to B. What this theorem is basically telling us is, let's call that C. We'll call this A. We'll call this B. I could integrate from A to C, that's this guy, plus I could then integrate from C to B. And guess what's true about those two areas when you add them together? It's the whole big area from A to B. Next one, this one's easy. If you have a constant, guess where the constant can go? You can pull it out to the outside. Here, if you have the sum, the integral of the sum of two functions, it's simply the integral of their sums. It's like the distributive property, which we mentioned yesterday. I can distribute this integral to both of those functions. So these, I think, are pretty intuitive. I would say this one's pretty intuitive. This is the one that students tend to forget, so I might note that in my notes. So let's see an example of all of this right now. Okay, doing good on time. Remember, guys, I'm going to try to limit myself to 60 minutes, and then the last 30 minutes will be questions and support time. So I'm trying to evaluate this integral from, in the lower limit of integration is 3, the upper limit is, the lower limit is 1, the upper limit is 3. The function here, this is the f of x, if you will. This is f of x, so it's 3x squared minus 2x plus 5. This is what we call the lower limit of integration. This is the upper limit of integration. So this is telling us where we start. This is telling us where we stop. This is telling us the variable in which we're integrating with. And now it says, use this information to find that answer. Now I'd like you to think for just a second about how else we could do this problem. If we wanted to, we could do the limit as n goes to infinity, the sum from 1 to n of f of, in this case, so that'd be, let's just write, I'll just put f of c sub I, and then delta x here, right? I would like you to think about how fun that problem would be with this example. Wouldn't that be fun? That would not be fun. In fact, I don't know that any of us in this class, maybe even myself, would get it right. I'd probably screw something up. The good news is this problem gives us the following information. So now what I'm going to do is I'm going to use this information here, and I'm going to use all of these properties on this slide to find the answer to this problem without actually doing any integration. I'm just going to use the properties of integration. So let's just go ahead and start this. So I'm going to go from 1 to 3 of 3x squared dx minus the integral of 2x from 1 to 3 dx plus the integral of 1 to 3 of 5 dx. Would you guys agree? I went from this to this. Do you guys understand how that works? Which of these properties did I just use? Did I use 1, 2, 3, 4, we'll call this one 4, or 5? Which property did I just use? 5. I used this one down here. So I just undistributed, if you, or actually I didn't undistribute, I distributed the integration. Would you guys agree? Does that make sense? So that was property 5. I can go further. I can say 3 integral 1 to 3 of x squared dx minus 2 integral 1 to 3 of x dx plus 5 integral of 1 to 3 dx. And let me make sure, I should have done that in a different color. Let me fix this here a little bit. I'm going to get rid of this guy. I'm going to get rid of this guy, this guy, this guy. I'm going to make them a different color just so you guys don't get confused on what I'm doing up there. Let's do green. So this is 1 to 3. This is 1 to 3. This is 1 to 3. So, okay. You with me? Oh, by the way, what property did I use there? Number 4. I used property number 4, which says I can pull that constant out. So this was property 4, or this was property 4. This one up here was property 5. Guess what I can do now? Well, let's look here. Let's do it in blue. What does this integral equal? Well, this definite integral equals 26 over 3. So this is 3 times 26 over 3 minus 2. What does this integral equal? Well, it tells us right there, 4. Need to do parentheses here. And then the last thing here is plus 5. What's this integral equal to? It tells us 2. Now, I made this one up convenient for me because guess what happens to these 3's? They cancel. So you get 26 minus 8 plus 10. 26 minus 8, I think, is 18. Plus 10 would be what, 28? You might see something like this in the future.
Well, what if we weren't given those problems?
Yeah, Rachel.
So, on every problem like this, is there going to be like those 3 other?
You would have to be given enough information for you to do that. Now, Rachel, I'm going to be completely honest with you. If I give you this problem next week, you won't have to use any of this stuff because you're going to know the fundamental theorem of calculus. I just haven't told it to you yet. In other words, you could do this problem without doing, I'm kind of giving you guys a foreshadowing, yeah, that's the right word, foreshadowing of what's going to come. You know, you could do this. We're not going to do that today. Okay, we did that yesterday. You could use these properties like I just did. But next week, I'm going to show you how to do this without any of that. I'm going to give you an even more powerful shortcut. It's called the fundamental theorem of calculus. Okay, where's my clicker? Here it is. Any questions out there in virtual land? Okay, guys, again, what I'm trying to do is lay the conceptual groundwork for what we're going to do next. The next 2 weeks, we're going to be in section 4.4, which is the most important section in the entire book, called the fundamental theorem of calculus. Okay, so here I've got a theorem. This is theorem 4.4, and it says continuity implies integrability. Wow, that sounds like some fancy words. Here's what it's telling you. If a function is continuous, then you can integrate it. That's all it's saying. It's telling you that if a function is continuous, ooh, let's do that in red. If it's continuous, then that implies you can do the integral. I'll just put a number. If a function is continuous, then you can integrate it. That's what it's telling you. Okay, virtual students, I got a question for you. We had a similar theorem about differentiability or differentiation. Would you please write in the chat what you think that is, if you know it? If you don't know it, just don't type anything. I'm going to mute myself, and so you guys here in one here in class has been able to identify, and no one in virtual land has been able to identify. And here's the point I'd like to make. I'm giving you this theorem. No one remembers what this theorem is. So here's my question. Correct. Gaia, you are the gold brick winner for the day. Gaia, I'm going to award you a gold brick, even though I can't physically give it to you, Gaia. I'm awarding you this gold brick, and here's what I want to commend you on. So right now we are living in a very interesting time, and we're living in a time where we know that pretty much everything that we do, you know, you guys are virtual. So like when I give you the quiz here in a couple of weeks, you guys can have a reference sheet and, oh, I don't need to worry about that stuff. I don't need to memorize that. Oh, I'm good. I'm telling you what, guys, you want to do well on the AP exam? Know your stuff. If you don't know your stuff, it does you no good. And I'm telling you what, on the AP exam, I think it was 2 years ago, there was a question worth a point, and I know that doesn't sound like much, but that could be the difference between a passing score and a non-passing score, that basically said that a function, it says that f of x is differentiable. Blah, 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 blah. And then it asks some questions. But one of the questions, I'll say part C, is something about how do you know it's continuous? Guess how you know it's continuous? Because it was differentiable. Now, I also am bringing a point about this. By the way, Gaia, good job. Because notice that for integrability, it says continuity implies integrability. But back in chapter 2, it said differentiability implies continuity. Do you see how it kind of went the other way? Here it's continuity implies integrability. Down here it was differentiability implies. You guys remember P arrow Q, right? Does P arrow Q mean that Q arrow P has to be true? Nope. Okay. One final thing here. We got about 3 minutes left, and then I'll give you guys your. Say again.
What did she say that was right?
Differentiability implies continuity. And by the way, that's actually the name of the theorem. Last thing I want to mention here, we've got about 3 minutes left, okay? And actually, you know what I think I'm going to do? For you guys that are in virtual land, I'm going to go ahead and give you the exit ticket now. So if you want to work on that, copy, I'm going to go ahead and put it in the chat. You might want to think about that video that I posted in the announcements. If you want to be a really successful math student, there's some really good advice. Okay. So this is another thing that is fairly common on the AP exam is they'll tell you, you know, hey, this function here, here's the graph of g of x. And they might ask you now to then calculate these definite integrals. And remember, what is a definite integral? It calculates the area under a curve, right? Calculates the area under a curve. So what the heck does this mean right here? This is saying calculate the area from -2 to +3. So starting right here, here's -2, and then 1, 2, and here's +3. Calculate starting from -1 to 3 of our function g of x, but they want us to do 2 times that. Now, based on our properties, where can that 2 go? It can go to the front. In other words, this would be 2 integral from -2 to 3 of g of x dx. Now, here's my question. How do I calculate that? How do I calculate this based on this graph? Notice they didn't tell us what the function is. They just gave us a graph. Well, what does the definite integral do? It's all about area, isn't it? What's this shape? It's half of a circle. So to find this area right here, I just got to do pi r squared divided by 2 because it's half of a circle, not a full circle. What's this shape here? It's a triangle. How do you find the area of a triangle? 1/2 base times height. So here's my question. Can I find the area of this half circle? Can I find the area of this triangle? And then guess what I have to do with those two areas? Add them together, right? I got to take this area plus this area. Remember, an integral is a summation. Add those two things together. Oh, and then by the way, don't forget to do what at the very end. So let's go ahead and do that. By the way, what's this radius? It's 2, isn't it? So this is -1, that's 0, that's 1, and this is 2. So this radius here, r is equal to 2. So to find this, and let's do that in green, I'm going to do pi times 2, which is the radius, squared divided by 2. And guess what happens to one of those factors of 2? It cancels, so I think you're just left with 2 pi. Would you guys agree with that? So that's the area, that's this area right here. How are we going to find that area? Well, we got to use this formula. So this one, I'll call this area 1. There's area 1. So how am I going to find area 2? Well, I got to do 1/2 times, what's the base length? Well, it's 1. What's the height? Let's see here. It's 1, 2. Oh, it looks like it. Oh, it's 3, right? So that's 3. So what's the area of the triangle? Well, what's 1/2 times 1 times 3? 3/2, I think, isn't it? Do you guys agree with that? Does that make sense? So what is this total area here in blue? Well, it's 2 pi plus 3/2. That's what that total area is. Oh, but don't forget, I got to multiply this whole thing by 2. So it's going to be 2 times 2 pi plus 3/2. So I think that's going to be 4 pi plus 3. So that's one example. Now, guys, we're kind of at time now, so I'm going to stop here. Here's some other examples. Like this one, it says that. Notice it doesn't say -7 to 0. It says 0 to -7. So we got to be careful. We're going to have to use that property with the negative. Here, oh, that's an interesting one. Here we're taking the function, we're actually increasing it by 1. And then the last one involved absolute value. I can talk about those during the extended time, but we are now at that 60-minute mark. So we're now at our 60-minute mark. So I'm going to go ahead and stop recording. And for those of you guys that are in virtual land, if you would make sure you would please finish that exit ticket so you can give me some feedback on where you're at with some of this. And that will be that. I will stay on here for the next 30.